Okay, welcome everyone. So what we're going to end up doing is talking about the MIMC chart and IMF's intermolecular forces. So it's going to be a quick little run through of the notes here. So IMFs, let's start with that. What are intermolecular forces? They're the forces where? Between the molecules. Awesome. And so we know that they're not, it's not inside. Inside would be called intramolecular, but between these two are called the IMFs, or the intermolecular forces. So we know that intermolecular forces are more easily broken than intra, and we'll talk a little bit about that in just a second here. So we first had started by talking about polarity and how the molecules will either be nonpolar, they'll be polar, or they'll be ionic, where they completely exchange and transfer the electrons. In polar, the electrons are not shared equally, but in nonpolar, they are shared equally. And so when you have a polar molecule, it creates this type of pull in one direction. What do we call this? Dipole. Awesome. So the dipole moment, or the dipole. And if that dipole moment does not cancel out, then you have a polar molecule. Okay. So we have three different types of forces. We have LD, London forces, or dispersion forces. Those are the weakest of all of them. These are in every single type of molecule. Okay. But they are specific to nonpolar molecules. So if you have a nonpolar molecule, it only has London. It only has London forces. Dipole-dipole is for polar molecules. But if it's a polar molecule, it'll have dipole-dipole forces, but it will also have London forces. Okay? The third type is hydrogen bonding. That's a special case. Remember, hydrogen bonding is a type of dipole-dipole, which means if you have hydrogen bonding, you have dipole-dipole and you have London. So if you have hydrogen bonding, you're going to have all three. You're going to check all three boxes. Okay? And the hydrogen bonding is specifically when you have hydrogen bonding to the force is between hydrogen of one molecule and what three elements? F-O-N, phone. Perfect. On a different molecule, on another molecule. Okay. So then this was just showing the LD force. It's very temporary. It's very weak. And what we had ended up talking about was the fact that as your molar mass increased, it really is the number of electrons that you have. The London dispersion force actually increased as well. There was a stronger force between the molecules. And if you have a stronger force, then what happens is the molecules are held more tightly, and it's harder to get them to separate and boil. Because what is boiling? If you have a liquid, those molecules are floating past one another, but they're still connected by a force. What do you do when you turn a molecule into a gas? What do you do to the force? Completely break that force. That force is now gone. Okay? And so boiling it is breaking that IMF. Not the intramolecular force, but the intermolecular force. And so what we see is, as you increase the molecular weight, the boiling point also increases. So that's going to be something that you're going to want to make sure that you remember here. But that only works if it's just LD forces. If you have another force, a stronger force, like let's say a different molecule has a dipole-dipole force, that's going to predominate. You're going to look at that first, because its molecular weight isn't as important as what type of force it has. And I'll show you that in just a second here. The dipole-dipole force, that we go, there's a polar molecule, another polar molecule, and the dipole in between. And hydrogen bonding is specifically hydrogen with F-O or N, same thing as a dipole-dipole force. Okay, and so this is showing this where we see that the molecular weights are increasing and the boiling points are increasing, but it didn't work for these three. These three have lower molecular weights, but their boiling point is higher. And the idea was, what IMF was predominating there? What was taking over there? Hydrogen bonding. And so these all have hydrogen bonding, so not just dipole-dipole, but hydrogen bonding, and so those end up having a higher molecular weight. And that was pretty much the same thing here. Now, the last thing that I want to make sure that we look at is there is one more type of force. It's actually down here. There's one more type of force, and this is not called an IMF because IMFs are specifically for molecular compounds. But for metallic and ionic compounds, these have higher, even higher boiling points than the other ones do. And so if we look at this chart, we can see that the boiling points with the London dispersion is at like negative 188 Celsius. And then as we get to like hydrogen bonding, it's at like 65 degrees Celsius. But then you see this huge jump, 1500 and 1700 for the boiling points. And why? Because metals and ionic, it's not the IMF anymore. What is it called? An electrostatic force. Okay? These have a stronger, which gives them those higher boiling points. So that electrostatic force, which is the opposite, positive, negative, where they completely transfer the electrons, that ends up being a stronger force than this weak IMF that's between the molecules. Okay, so now let's shift gears and let's take a look at the MIMC chart. Let's review on the MIMC chart. Okay, this chart is for solids. The question is, if you found a solid in nature, if you found any solid, then how does it exist, okay? And there are really two ways that it can exist. It can either be crystalline, which means that it's in an orderly repeating pattern, so the atoms or the molecules are orderly repeating, or it can be amorphous, okay? And amorphous means they're not arranged in an orderly pattern. So glass and wax and rubber would be amorphous solids, okay? These are all crystalline solids. These four are not amorphous. This is it for amorphous. We're done. Get it out of your head. These are all what? Crystalline, okay? These are all going to be crystalline. So the first one is metallic, and I really like this one. The metallic ones are held together by what they call a sea of electrons. So what you can see is it's positive nuclei, and just like if you had fish in the sea, you don't know, the water is surrounding all of them. The electrons are surrounding all of the nuclei here, and you don't know which electron belongs to what nucleus. So you get something like silver. If we look at silver on the periodic table, silver has 47 protons, okay? And so if it has 47 protons, then how many electrons would a neutral atom have? 47. And so you would have a little tiny nucleus, and then you'd have 47 electrons. But you can't tell, once you start putting your electrons, filling your electrons around, you can't tell which one belongs to what nucleus, okay? And so that's the sea of electrons model. Well, what is significant about that? We know that electricity happens because you have a flow of electrons. Good. And so what you can get here is you can get movement of the electrons across, and that's why this, the metallics will always conduct electricity, always conduct electricity. There's no, that's it. It is what it is. Okay, those will conduct electricity. So they're held together by positive nuclei with the sea of electrons. They're good conductors because the electrons are free to move around. We see that they're malleable, which just means that you can reshape them. Okay, so you can hammer them into different shapes, and it's any metal in the periodic table. Ionic solids, these are held together electrostatically. So are metallics. So are metallics. Those are also held together electrostatically. So just to make sure that you know that. And so this says it's just a slice through an NaCl crystal. And so you can just see that it's alternating positives and negatives. These are good electrical conductors when they're melted or in water. Not always. They're not always. If you have salt inside of a container and you try to conduct electricity with the salt, it will not conduct electricity. Why? Because those ions are not free to move yet. If you dissolve them in water, what happens? What happens to the substance? It starts to dissolve and breaks up into ions, and those ions start to move. And once those ions start to move, you can get electricity to move across, because what do you have free now? How do you get electricity to move? Electrons. Awesome. As long as you can get movement of electrons across, then you will be able to conduct electricity. Okay? And so these, the ionic bonds are very strong because they're electrostatically attracted. They have high melting points, and then examples would be like NaCl, Mg, any of the ionic compounds that you're used to, and the metals are any of the metals that you're used to. And typically it's a metal plus a nonmetal, or a cation plus an anion will also be a correct answer for that line. Okay? Molecular solids. You are going to recognize these on the chart because these are commonly going to be in the gaseous or the liquid state, not in the solid state at room temperature. You do not typically expect to find these. Why? Because they have weak forces. And if they have weak forces, they separate really easily. And so the molecular solids at room temperature are typically a gas or a liquid, like carbon dioxide. Okay, so like carbon dioxide. Now, the reason why I bring up carbon, you're going to see that carbon will also form what is called network covalent. So people will get confused and say, how am I supposed to figure out if it's a molecular solid or if it's a network covalent? Because carbon can do both, okay? All I want you to do is check to see, is this something common that you know, like carbon dioxide or like carbon monoxide? Or, you know the Matt eats peanut butter, the alkanes? Yeah. So like methane, ethane, propane, butane, those like CH4, C2H6, all of those compounds, for example. What phase do you find those in? Well, you guys know propane, for example, comes in like a tank, in those big tanks. Yeah. If you know that methane comes out of the gas valve, right? So we know that that exists in what phase? A gas, okay? Some of them will be liquids, like the alcohols, for example, could be in the liquid state. But those at room temperature are going to be weaker forces. And then I'm going to go to covalent network in just a second to tell you the difference, okay? So these are held together by weak IMFs. Typically, these are going to be non-metals bonding or water with the non-metal. Sometimes a metalloid with a non-metal can form molecular solids. Low melting points, just like we said, and examples are water, dry ice, like carbon dioxide. So when you get dry ice, like at Meyer, they have a huge container. You have to wear gloves to get in, and you can get the dry ice, but it sublimes at room temperature. And so if you just leave it sitting on a counter, what does it skip? It goes straight from the solid to the gas phase, okay? And so it has that weak of forces that it actually just wants to separate right away. And sulfur and iodine would fit under molecular solids. Okay, covalent networks. These are giant, they're huge, large molecules that are covalently bonded. So these have electrostatic forces, and this we know just has IMFs, okay, whatever type of IMF depending on what type of molecule, if it's polar, if it's non-polar. But these have covalent bonds in between, okay? So that's going to be a lot stronger. We said that a covalent bond, in comparison to an IMF, they're about 10% the strength of a covalent bond, okay? So these are going to be a lot stronger. What do we see? We see things like diamond, which is made of, anybody know? Carbon. The special thing about diamond is that each carbon atom is actually bonded to 4 other carbon atoms. So if you were to look closely, covalently bonded, so meaning they're sharing the electrons. So these are all bonded with each other, and then every single one has 4 that it's attached to. Graphite is also made of what? Carbon. This is your pencil lead, okay, what they call the pencil lead, right? But what you can see is this is a lot weaker, but what phase does this exist in at room temperature anyway? Solid. So you know that if you get something like this, like carbon in the diamond form or carbon in the graphite form, it's going to be a lot stronger. It's not going to be a molecular solid. The molecular solid should be in what phase at room temperature? Yeah. Gas or liquid, okay? Versus this is going to be in the solid state. Diamond is the hardest substance that we can find on Earth, okay? That's the hardest that we've ever found. And graphite isn't really, and you can see the structure's a little bit different. What happens is in here you have space, okay? So these would actually be forces that are holding these two together, but these are held together by covalent bonds. You get covalent bonds, then you get space with IMFs, covalent bonds, space with IMFs. So that's why it's not as strong as diamond would be. These are called Buckminster fullerenes, or buckyballs is what they call them. And this is also fullerene. These are carbon nanotubes, where it's also carbons in chains. They use these on like in productions of planes, for example, too, on the outside of a plane. Okay, so these are different, what they call allotropes. So it says allotropes are just different forms of the same element. And so these are different allotropes of carbon. Okay, let's come back up to the covalent networks. So they're held together by a large network of directional covalent bonds. They act like one giant molecule. They have high melting points, again, because those bonds are so strong. And examples are diamond, graphite, silicon, and germanium, and they're usually metalloids, okay? But what I want you to think about is, like, for example, SiO2 is sand or quartz, and if you see Si, if you see silicon, it's a metalloid. And so you're going to question and say, well, I don't know, is that going to be network covalent, or is that going to be a molecular solid? But if you know that sand and quartz, which is a type of rock, right? If you know that those are in what phase? Solid, then that's probably covalent network, okay? So that's going to be your way of guessing. Okay, so I really quick just want to show you one more thing on the IMF and intro worksheet that's on Google Classroom. So this is just showing hydrogen bonding, and so we see the attractive force here, and it's hydrogen of one compound or one molecule, and then phone of another molecule. And again, just like we talked about the dipole-dipole with the polar molecule at the dipole and another polar molecule, and then you get the attractive force in between. And the LD force, which is very temporary, and so you can have any molecule and any molecule with the attractive force. That's the weakest of all of them. And the last thing that I wanted to make sure that we just looked at, because you need to know this, is what is called the ion dipole, okay? So the ion dipole is a little bit different, just like electrostatic forces are a little bit different. What you end up having is you'll have an ion, either a negatively charged ion or a positively charged ion with a polar molecule, okay? And this is what you call the ion dipole force, okay? So you can see here, this could be like S2 minus or F minus or Cl minus, or it could be a polyatomic ion, okay, with a negative charge. And there's an attractive force between that negative ion and the polar molecule, but what side of it? Well, if this is negative, what side is it going to be attracted to? Positive. The partial positive side. And so you can see, like, if you had a polar molecule, like SO2, for example, whichever side is more electronegative, it's going to get attracted to that side. And the ion dipole works the same way if you have another polar molecule, but then with the positive charge of an ion. So this could be a calcium ion or a sodium ion or a lithium ion. If it's a polyatomic ion, the only one is NH4 plus that we have that's a positive charge. So just wanted to make sure that we also highlighted the ion dipole, because you do need to make sure that you know that too. But that's it for a quick little review of IMF and